All right, students, this video lecture will serve in place of an in-class lecture for Wednesday, January 31st, 2024. We're going to resume where we left off, and it will be expected that students will watch this. This is what you should be watching instead of coming to class on the aforementioned day. And so once we resume, ideally, I'm fully planning on normal class resuming on Friday for us. We will pick up right as this one ends off. So it is expected that students will watch this. Make sure to treat it kind of like a normal class, just in terms of your note structure. I will open the floor up on that day for any questions from you guys. Absolutely. But the expectation will be that you guys will have watched this recording and that you've gone over all of the sample questions in here. And I have already done out work for sample questions since I'm not in front of you with the board. You'll see how that looks as we go on. But again, any questions and any needs or concerns, do please let me know at absolutely any time, either via email or whenever you see me again on Friday. Now, where we left off within Chapter 3, Chapter 3 was about motion and the ways that we describe motion. We went over displacement, velocity, and acceleration, and we looked at this family of 4 formulas here that we use to describe one-dimensional motion. And just to briefly review them, this first formula here is the definition of velocity. Velocity is the change in displacement over change in time. And the second one is the definition of acceleration. Acceleration is defined as the change in velocity over the change in time. And then these two formulas here, the number 3 and number 4, talk about the relationship between acceleration and displacement. Because while you're accelerating, not only does time pass, you are also moving through space while that happens. When you hit the gas, you do have to move forward as you're speeding up. And so that's what these two formulas down here represent. They have similar uses, but which one you use in any given scenario just kind of depends on, maybe if you know time or are looking for time, you use Formula 3. If you don't know time and don't care about time, then you might want to use Formula 4. We looked at a few examples using these, and I want to look at least one more before I also move on to Chapter 4 in this particular set of notes. So this lecture, we will be concluding Chapter 3 and also doing Chapter 4. Namely, I want us to do another example involving falling. We began looking at and using these equations to describe the act of falling, and that's because on planet Earth, falling is an acceleration. If you are in the state of free fall, you are accelerating towards the core of the Earth, technically at a rate of 9.81 meters per second squared, but for simplicity's sake, whenever we don't need very precise measurements, like in lab, I might have you use 9.81 sometimes, and I will always remind you when those scenarios are. But for general use cases, like in lecture and definitely on tests, we're going to stick with 10 meters per second squared. We're just rounding up for simplicity's sake to make the calculations a little bit easier. So for this class, if something is falling, if it is an object in free fall, that automatically means it is accelerating at a rate of 10 meters per second squared towards the ground. And since that's always going to be down, I'm commonly going to write this as g equals negative 10 meters per second squared. We did at least one falling example using this number along with the previous equations, but I want to do one more before Chapter 3 wraps up and before we move on to Chapter 4. So, as another example, because interestingly, something can be falling even as it is rising, interestingly. And that's one of the scenarios we're going to explore here. So this next example, a basketball player leaves the ground with an upward velocity, an upward speed of 6 meters per second when they jump vertically upwards. First question that we will address is how high do they jump? Second question is how much time will they spend in the air? And interestingly, you can be falling even as you rise, because the definition of free fall, if I back up a sec, the definition of free fall is the state when gravity is the only force acting on you, and you begin accelerating at that negative 10 meters per second squared. And that can begin happening on the way up. Because once your feet leave the floor, in this particular case, since we're talking about someone who's jumping, once your feet leave the floor, the supporting force from the floor is gone. When you're standing on the ground, the upward normal force from the floor is what's holding you up and supporting you against the force of gravity pulling you down. But once you leave the floor, that vanishes. The floor can't exert force on you if you aren't touching it. So once you're in the air, the only force acting on you is the force of gravity, is your weight. And so even as you rise up to that highest point, which I call the apex sometimes, the apex of your leap, you are already falling even on the way up, because even on the way up, the force of gravity is the only force acting on you, and you are still accelerating at a rate of negative 10 meters per second squared. I'm going to tab ahead to a graph real quick. The editing on this slide's a little off. I apologize. I mostly just want to look at this graph right here. And this kind of is meant to show the both vertical and horizontal velocities of something that has been thrown up into the air. And you've probably thrown stuff like this too. This is just meant to kind of replicate throwing something up and then it coming back down to your hand. Once it leaves your hand, it's now in a state of free fall. And so every single second that passes, you can see here that between each of these frames, notice here it's got 0 seconds, 1 second, 2 seconds, 3 seconds, all the way down to 6. Each of these kind of represents a different moment in time, kind of like you're watching the frames of a video. And the arrows, these red velocity arrows, are meant to represent the instantaneous velocity of this particular baseball during each of these 1 second frames. Note that once the ball leaves this person's hand, it's at a pretty good upward velocity, but every single second that passes, that upward velocity shrinks. The arrow got smaller here, even smaller here, and now at 3 seconds, there just isn't an upward velocity at all. Because this point, the apex, that's the point where you have accelerated to a standstill. And every object does this when you throw it into the air, and therefore, by extension, this also happens to you when you jump into the air and you hit that highest point. When you hit that highest point, that is the point where your upward velocity has accelerated to 0. You start with an upward pointing velocity, but since your acceleration points down, that upward velocity shrinks to 0. And this moment, the apex, that highest point, is the moment when that upward velocity is 0. And this happens every time you throw something. Whenever you throw something straight upwards, that highest point, the object technically stops for a second. It's kind of hard to perceive with just your eyes, but for a brief moment, the object is just stopped. And then once that moment passes, gravity still keeps pulling the object back down. And so every second after that, the object is falling down. It was already falling while it was moving up, technically. But every second after that, the downward velocity of the object starts growing until we get back to this point and the object is, back at the same height it was at before. Note the vertical axis here is on the graph is showing height over time. And at this particular point, the ball is back at the starting height of 0, and its velocity now points down. Because gravity is an acceleration downward. So what that acceleration did is it caused this initially upward velocity to shrink to 0 and then to become negative. And it's worth noting that this negative velocity, this pink arrow here, is the same size as the initial upward velocity. Because if something is thrown and then it falls back down to the same height, generally speaking, its downward velocity at that moment will be the same as the upward velocity. If this person threw the ball upwards at 10 meters per second, then by the time it reaches their hand again, its top speed should be negative 10 meters per second because it had the same distance falling down to accelerate as it had rising to accelerate. And that's going to be something that we explore with the math for this the leaping athlete in this particular question. So kind of with all that preamble out of the way, let's kind of start dissecting the math of what happens here. Basketball player leaves the ground with a speed of 6 meters per second when they jump vertically upwards. So the initial velocity is going to be 6 meters per second up. We're going to figure out how high this person jumps and how much time they spend in the air. So I'm now going to show you my work for this. Feel free to pause at any time or try to zoom the picture in. And again, we can refer back to this in class if my handwriting is too difficult to read. Please let me know, again, at absolutely any time. I've kind of replicated that graph here that I showed a second ago just to kind of re-demonstrate and put onto this slide what I mean by this. This is a height versus time graph where this person is going to jump up into the air. They're starting with an upward velocity of 6 meters per second. And whenever they reach that maximum height that we're going to find, at that specific moment, their velocity will have shrunk to 0 in that moment. And then they're going to fall all the way back down. And at a certain point, right before they hit the floor, they'll be moving at their highest downward pointing speed, like right before impact. And that final downward speed should be negative 6 meters per second. Because if they leave the floor at 6, they will come back to the floor at 6, but in opposite direction. And that's because they have the same distance on the way up to slow down to 0 as they have on the way down to speed up from 0 back to the original, because the acceleration is the same magnitude in both directions. Again, we'll be looking at the math for that. Whenever I do work on the board in class, I'm in the habit of writing out my variables, so I've started writing out various things up here. First, we've got our initial velocity, VI, listed at 6 meters per second upwards. Next, I've listed 2 different final velocities. First, writing out again, at this maximum height right here, the instantaneous velocity at that point will be 0 meters per second. At that highest point, you freeze for a moment. And separately from that, and so I wrote here V at max height. That's meant to be the at symbol. And then here, this is meant to say V at floor. So this is the speed or velocity as we return to the floor, moving at that fastest negative 6 right before impact. That's before we actually touch down. So like we don't lose any velocity yet. This is the fastest rate right before impact. Additionally, since this person is falling, and again, they are falling on the way up, since they're falling, we automatically know their acceleration. If something is falling, or someone is falling, their acceleration will be equal to the acceleration of gravity, and that is automatically negative 10 meters per second squared. I am just now realizing I left the square off there. Let's see if I can draw that in. It's okay. But note, that should say 10 meters per second squared. I apologize. Acceleration should be measured in meters per second squared. And the 2 things we're looking for here are maximum height, which I'm going to call delta y max, the biggest change in our biggest change in position from our starting location. And also we want to know the total amount of time in the air. So, with all that said, we've got everything listed out. We know V initial. We've got kind of 2 different reference frames for V final, depending on which moment we're looking at. We've also got acceleration, and we are looking for delta y and t. Now, to that end, again, it's usually a good idea to draw pictures, list out your variables, and then to find formulas that contain the variables listed here. And so I went ahead and listed out a couple of formulas to look at, namely formulas 3 and 4 from that previous slide, from the Fantastic Four slide. And that's because, again, while you're falling, accelerating, that's the A terms, you are moving through space, you are displacing. So these formulas talk about how you are displacing through space while accelerating and falling. So I listed those 2 formulas out. We'll just take a look at how useful they might be to us so far. First up, delta y, formula 3 right here, delta y equals VIT plus 1/2 times acceleration times time squared. Now, within this formula, the 2 things that we're again after are delta y maximum. We want to know the biggest change in position from the floor to the maximum jump height. And we also want to know the total amount of time spent in the air. And in this particular formula, we do know initial velocity, so we can put in 6 here. We know acceleration, so we can put in a -10 there, but we don't have anything for delta y or t yet. So this formula right now still has two unknowns in it, no matter what frame of reference, no matter which variable we're looking for, or which kind of moment in time we're looking at. And so this one we're going to kind of put a pin in and come back to later. This second formula, though, or rather the fourth formula listed on the Fantastic Four slide, this one, though, again, I mentioned earlier that this one's useful in cases where you don't know time, and we don't know time yet. That's kind of one of the problems. We don't know time, but there's still time in this formula, so we can't use Formula 3 to solve for delta y. But this one, it has delta y in it. It has a and velocity initial and another term in it, but no t. And so not knowing time means that it doesn't interfere with this formula. So we don't know any time measures yet. That doesn't matter here. We can still solve for delta y. We just need to make sure that we have acceleration, initial velocity, and final velocity. And we actually do. Mentioned again, if you're falling, you're accelerating. So we know the acceleration. We know the initial velocity because this person's going to jump upwards at 6 meters per second. And interestingly, we actually do know the final velocity because I've got kind of labeled here two different groups of calculations. This first group here is at max height. This is the calculations that I plan to use to find the maximum height that this person's going to jump to. And we actually know their final velocity at that highest point because, again, at that apex, your velocity shrinks to 0 for a second. And so if you are looking at a projectile motion question like this, projectile motion is just a fancy way of saying the motion of a falling object. If something is falling, it is a projectile. And that can include, again, jumping humans, because once you leave the floor, you are falling, and if you are falling, you are a projectile. And so this is true for all projectiles, all falling objects, and all falling people, or all jumping people, really, in this case. Once you reach that apex, you're not going up any higher, you do stop for a second. The velocity at that moment is 0. And so we can treat that as our final velocity to be able to solve for delta y in this particular case. Because again, if we plug in a 0, if this moment is our final moment, well, that's the moment where we're at the highest point. So that makes sense. If we plug in the final velocity at this moment, then we'll find the displacement, the jump height, at this moment. So what I've done down here is I've taken the same formula, Formula 4, and I've just started plugging everything in. Again, the final velocity at that highest point is going to be 0. The initial velocity is going to be 6 upwards, and the acceleration is going to be -10, specifically negative because we are accelerating down. Again, vector direction is important. We need to separate this downward acceleration from the upward pointing velocity. It's very important contextually. And I've left delta y as it is because that's the unknown that we're going to solve for. Now, 0 squared is just 0, so that's just going to kind of go away. 6 squared becomes 32, and 2 times -10 is -20. So this next line down, I went ahead and moved this 32 over to the other side. And so what I've got here is a simplified form of -32 equals -20 delta y. Again, that 32 is the 6 squared, just subtracted over to the left, and the -20 is the 2 times -10. And then to solve for delta y, we'll just divide both sides by -20. So we get delta y equals -32 over -20. And that's going to give us a maximum jump height of positive 1.6 meters. Just for context, that's probably that's at least 5 feet. That's approaching 6 feet. For a vertical jump, that's very impressive. So if you're like me and you can only jump about 2 feet vertically, probably, if I'm being honest, probably only about 1 foot in the air, your jump speed probably isn't as close to, 6 meters per second. Again, I can only jump about 1 foot in the air. My jump speed is nowhere near that impressive. So this is a star athlete. But that's the first part solved. We have now found the distance to that maximum jump height. They will leap a grand total of 1.6 meters up into the air. Excuse me. And at that distance, they will then start falling back down. So I've labeled all of this, kind of all of these together in kind of their own separate little branch here, indicating again, this group of calculations is for studying the at max height portion of this particular question. And now that we actually know delta y, we can actually take it and plug it into the formula 3 that we were talking about, because over here we got a little stuck because we didn't know delta y or t. But now we do have something for delta y. We know how high we jumped to, and if we plug that 1.6 in, we could solve for the time it took to get from the floor up until this point. And so once you plug that 1.6 in, t is the only unknown left. Now, this would require us to do a quadratic, and so I'm just going to let you know that this is something that you could do, but we'll just leave it here for now. Because technically this time isn't even the second time that we're after, because this time would be the time that it takes to get to the top, not the time it takes to get to the floor. Because if you plug in the delta y at the top and not at the floor, then the time you get will be the time it took to get to the top, not to the floor. And that's why I've separated the at max height calculations from the at floor calculations, because they're taking place at two different moments. Please let me know if you have any questions about that. But the 1.6 is the maximum jump height. And so now we're going to look over here at the time it takes to reach the floor again calculations. This is what I would call the hang time. Hang time is just the technical term for the time it takes to rise and then descend back to wherever you began. Or really, it's just the amount of time in the air. And so now we want the total time. We want to figure out the time it takes to go from our initial position up and back down to the same height. It's important to note that these 2 points, even though, they are scrolled away from each other on the graph, they take place at the same height. Note the vertical bar, the vertical axis here is height. And they start at the same position on the vertical axis because this point and this point are at the same height. This is the floor we start at, this is the floor we finish at. And that's actually going to be important to the math, because I'm going to use formula 3 here to help find the total time we spend in the air. That formula is, again, delta y equals velocity initial times time plus 1/2 times acceleration times time squared. Delta y in this case is 0 if we're looking at, again, overall the time it takes to get from here to here, because displacement cares about vector directions and where you end up relates to where you began. And so if you land on the floor and you started on the floor, your change in height is 0 as long as you end where you began. And so if we're using this formula to try to solve for time, that delta y term is 0 because we have ended back where we began. That's going to be important. The rest of the formula, again, we still know the same initial velocity. That didn't change. We're looking at the initial moment didn't change. We're just looking at a different final moment here. But that 6 meters per second upward is still true. T is still unknown, so we're going to leave that as is. And acceleration is still -10 because this person is still falling. And at this point, we once again have T is our only unknown, so we are set to use this to solve for T. This could actually once again lead to a quadratic, like I said over here. But we actually have something of a shortcut that we can utilize in this particular case. And it's because the entire left side term is a 0. Note, the entire left is a 0, and every term on the right has a t in it. And that means that if we divide both sides by t, that's not going to change the left at all, because 0 over t just becomes 0. And if we divide the right side by a t, that's going to cancel exactly one of the t's out from each of these two terms. So 6t divided by t just becomes 6, and 1/2 -10 times t squared over t just becomes 1/2 times -10 times t. There's no squared anymore. And after doing this operation, there's now only one t left. there's no squared, we don't have to do a quadratic anymore. So this is a very handy thing to note. You can sometimes escape having to do a quadratic when one of your terms equals 0. So that's an important math trick to be aware of. It's very useful. It's always useful when things cancel. And that means now there's only the 1t here. We can just solve straight on for the amount of time that this process takes. To do that, I moved... Technically what I did is I moved the 1/2 times negative 10 times t over to the left side. That's because the 1/2 times negative 10 would become negative 5. So I just added 5t to both sides to turn it into 5t equals 6. That means t equals 6 over 5, and therefore the total time in the air, the time to rise and fall back to the floor, is 1.2 seconds. 1.2 seconds. Kind of as a point of comparison, I've got an extra calculation down here. This is my attempt to solve for the amount of time it would take to rise up to this maximum point. So what I did here was I took formula 2, the acceleration formula. I plugged in the acceleration of gravity, change in velocity. Again, we start at positive 6 and we end at 0. So the delta V there is going to be 0 minus 6. And I solved for the time it would take to go from here to here. And interestingly, when you move delta t to the left and negative 10 over to the right, you get delta t equals negative 6 over negative 10, which simplifies to 0.6 seconds. I'm pointing this out so that you can note that this 0.6 seconds is exactly half of the 1.2 seconds. 1.2 cut in half is 0.6. And what that tells us is it takes 0.6 seconds to rise up to this point, and then another 6 seconds to fall back down. It's symmetric. As long as you are starting and ending at the same height, the time it takes to rise is the same as the time it takes to fall. And you will have your final velocity downward will be the same magnitude as your initial velocity upward. So there's just a couple interesting quirks about this scenario that I wanted to make sure that you guys had seen before, because I find them just very useful to understanding how falling works on planet Earth. But with those examples done, that is now the end of Chapter 3. And so now what we're going to do is we are going to move on to Chapter 4. It's a very short chapter. Chapter 4 is just about Newton's second law, so we'll be able to speed through it pretty quick. But once again, any questions at any time, do make sure to ask them. Even if you pause right now to send me an email or just write down something that you were curious about. Again, send me any questions. And what we're now going to do is switch gears and look at Chapter 4. All right. Now, as I said, Chapter 4 is about Newton's second law. We've been kind of spending one chapter at a time looking at each of the laws of motion, kind of adding an extra chapter in for 3 to talk about motion itself. But now in Chapter 4, we're back to the laws proper, and we're going to be looking at Newton's second law today. Just to kind of quickly review what the laws are and what they say, just kind of as a whole. Law number 1, law of inertia, says that an object at rest stays at rest, and an object in constant motion stays in constant motion unless acted upon by an outside force. The law of inertia, we talked about equilibrium states. The second law, the one that we're focusing on right now, says net force equals mass times acceleration. And law 3, for every action force, there is an equal and opposite reaction force. So let's focus on that second law. Net force equals mass times acceleration. If non-zero net forces are always the direct cause of acceleration in matter. And to kind of take this back to Newton's first law for a moment, if something isn't accelerating, then it is not... Sorry, even when I'm doing lecture recordings, sometimes I just need a moment to catch my breath and do water. Sorry. Had to reformat something as well. So, if an object is not accelerating, that means that the net force acting on it is 0. If acceleration is 0 within this formula, if you plug in a 0 for A, that means m times 0 is 0, net force is 0. If something is not accelerating, then the net force on it is 0. And again, net force is the sum of every force present. There's really no way to have no forces at all acting on something. Instead, if something is at equilibrium, it means that all the forces present add up to 0. And that's what we spent chapter 2 talking about. But today we're going to look at what happens when the forces don't necessarily add up to 0. If the net force doesn't add up to 0, if this is not 0, the object is going to start accelerating. It's going to begin accelerating in the direction of the net force, in the direction of whatever breaks the equilibrium state. And what the formula kind of overall says is, the bigger the net force, the bigger the acceleration, and also the bigger the mass, the more force is required to get it accelerating. Again, I did Taekwondo, and I actually learned a surprising amount of the laws of physics from my Taekwondo instructor. The way that he taught me this was, if net force equals mass times acceleration, force standing in for, punching and kicking strength, if you want to break a board, because I always had a hard time just breaking the boards myself. I had like a mental block on actually kicking hard enough to break the thing. If you want to punch or kick harder, if you want more net force, you either need a bigger M term, which would be either a bigger fist or a bigger foot, or you need a bigger A term. You need to just move your fist and your foot faster. And at least for me, that helped me get over that board breaking block. So, anytime that you have caused something to accelerate, it has been because that you exerted a non-zero net force on it. You exerted enough force to break the equilibrium state, and it's specifically the net force that determines acceleration. Single forces can only determine acceleration if that single force is or is very close to the net force, but it is overall the net force that specifically causes it. Let's use the formula a couple times just to make sure that everything makes sense. First up, we're going to apply force to a baseball. We're going to swing a bat and use 450 newtons of force to hit a stationary 100 gram baseball. We'll assume that 450 newtons is overall the net force. If the object was in the air, like it had been thrown at you, then gravity would be pulling down on it, but that downward gravity wouldn't be interfering with the sideways swing of the baseball bat, because again, vectors only directly add up in their own axis. So as long as the ball is in horizontal equilibrium before you hit it, the net force of 450 newtons to the whatever direction would still apply. So we're going to use this force on this baseball. We're going to calculate first the acceleration of the ball, and then secondly, what the ball's final velocity will be if that force is applied for specifically 0.05 seconds. Because it's important to note that forces and acceleration are only really happen for certain finite amounts of time. In the case of the baseball bat, the bat is only really touching the ball for a split fraction of a second. We'll look at the numbers for that now. So we got here, net force equals mass times acceleration. Our net force we're going to treat as the 450 because that baseball bat force is not really being opposed by anything. And it's going to act on the mass of the baseball to cause acceleration. Note here I plugged in 0.1 instead of 100 grams because for mass we always like to use kilograms. 100 grams is going to convert to 0.1 kilograms. And the formula lets us solve for an acceleration of 4,500 meters per second squared, which is a lot. That is a very big acceleration. But again, kind of for context, we're going to assume that this acceleration is only applied for 0.05 seconds, because every single collision, every single time force is exerted, it is only acting for a specific finite amount of time, and collisions tend to happen very fast. So this is a pretty realistic number for the amount of time it actually takes a crash to happen. And the bat hitting the ball does count as a collision. It does count as a crash. And so to find the ball's final velocity, I'm going to recommend using formula number 2, the acceleration formula. We're going to take the acceleration we just found, the 4,500. We're going to solve for the final velocity of the ball, assuming it starts at rest. And for time, we plug in 0.05. To solve for VF, we'll multiply both sides by 0.05. So we get 4,500 times 0.05 equals a final velocity of 225 meters per second, which is still a lot. That's about 2/3 the speed of sound. So, this is far and above what any actual baseball player could reasonably do, by themselves with normal human muscles. But I would just want to kind of draw the comparison here between the very big acceleration number and the more smaller final velocity, because this acceleration, this really big number here, only would happen for a very small amount of time. So that's just kind of a context thing that I wanted to mention. Now, to kind of tie back to the law itself first, net force equals mass times acceleration. That means that all three of these concepts are linked: force, mass, and acceleration. The size of the object, the mass of the object, affects how the force responds to it. So to kind of demonstrate that, we're going to take the same 450 Newton force and apply it to this bowling ball. And I don't know if you've ever tried to play baseball with bowling balls, but it doesn't go very well, as we're about to demonstrate. We're going to apply 450 newtons to a 30 kilogram bowling ball. We're again going to find the ball's acceleration, but we're also going to find how fast the bowling ball is moving if that acceleration is applied for 0.05 seconds. So, same formula. The only real difference is we're going to plug in a much bigger mass. Originally, we had 0.1 kilograms. Now we got 30 kilograms. And so the acceleration is a much, much smaller 15 meters per second squared. So since the mass of the bowling ball is literally 300 times bigger, the acceleration is 300 times smaller. And if we do the same thing with that acceleration and the time to find the final velocity of the ball, the final velocity here also winds up being 300 times smaller. This amount of force on this bowling ball does not cause the bowling ball to take off very quickly. So again, the mass of the object does matter. The same force can cause different responses if it's being exerted on two different objects with two very different masses. So wanted to make that clear. Now, we're going to start be doing more calculations with force, since we can now describe what forces do in equilibrium, but also now out of equilibrium, because Newton's second law describes a non-equilibrium state when something's accelerating. And so we're going to be doing more examples that contain force, and so I wanted to briefly mention some of the different kinds of force, because there's loads of different types. They all act as forces, they all work in newtons, they all push in a direction, they all do the same basic thing. But force can come from a lot of different places, and I just wanted to kind of go through these vocab words for a few different types of force real quick. First, though, is gravity, which we've already talked about. And gravity is a field force that acts between all objects with mass. The mass of your own body is being pulled towards Earth's core by the gravitational force of Earth's mass, and vice versa. All objects with mass do this, even small ones. It's just the smaller the object, the less gravity it exerts. And when I call gravity a field force, what I mean by that is a field force does not require direct contact. Things like tension, normal force, and friction, they all require objects to be touching in order to push on each other. But gravity doesn't need that. Gravity kind of happens if you're touching Earth's surface or you're not. So it's just another part of the vocab word. Tension, a different vocab word, is just specifically the force in a rope. When you pull on a rope, it's going to pull. If you pull outward on a rope, the rope pulls inward, and the amount of inward force the rope exerts is just called tension. So when I say tension, I'm really just meaning the force within a rope for the most part. Normal force we've talked about briefly. This is the term that I use to describe, some people call it the support force. When you push into something and it pushes back out, most commonly, when you push into the ground pushes back up on you and supports you, keeps you from falling into and through the ground or into and through your chair. This is basically the type of force that surfaces will exert when you press into them. And last vocab word for type of force is friction. I've mentioned this a couple of times now. Friction's kind of pesky in terms of how physics works. Friction is a force that objects exert on each other when one object attempts to move across the surface of another. Friction always opposes movement. The entire reason friction exists is to stop motion and make it just not happen, to either prevent motion from beginning or to make motion that's already happening cease. And in the coming days and weeks, we'll just be using different types of forces in different examples. One thing I want to note about gravity, because it's probably going to be the most common force we use throughout the semester. Every object on planet Earth, every object with mass on planet Earth, that mass is going to be pulled by a force downward towards Earth's core. Force of gravity is a synonym to weight. If I ask you for force of gravity, I am asking for the weight of the item. If I'm asking for the weight of the item, I am asking for the force of gravity of the item. They are the same thing. They are defined as one another. They are perfect synonyms. So right here, I've got weight equals Fg, force of gravity. They are not two different things. And it's important to note, objects with different masses will have different weights, but every object on Earth still falls at the same rate. I try to demonstrate in class that objects of different mass still fall at the same rate, still fall at -10 meters per second squared. The way that works is, if you want to calculate the weight of the object, you use this formula here. Fg, force of gravity, equals mass times lowercase g. Lowercase g is the symbol for specifically acceleration of gravity, listed here in the middle of the slide. And so we use this formula to determine the weight of an item. It is its mass in kilograms times the acceleration of gravity. We're going to use -10 for that. And objects with different mass will always have different weights. Like, if something has twice as much mass, it will weigh twice as much. But the way that those different weights still create the same acceleration of gravity. An apple and a bowling ball will both fall at this rate because the different weights are enough to pull their different masses at the same rate. The same g times a different mass creates the different weight. So the way that it works is, the g is the same for every item. If you double the mass, you double the force. Because the mass doubled, therefore the force of gravity will double. So the lowercase g, the acceleration of gravity, is the same for everything, and that does summarize why objects on Earth all fall at the same rate. So kind of a brief disclaimer thing there. And let's look at a few examples. This first one's actually going to be another equilibrium example like we've been doing, and then we'll kind of change that up afterwards. We've got a 100 kilogram crate that is suspended motionless in the air. Note again the word motionless. If it's in place, not moving, that means it's in equilibrium. We're going to calculate the force of gravity on that crate. We're going to find the force required to keep the crate aloft, and we're going to find the net force on that crate. So here in my work, I've got a free body diagram for the crate itself, mass of 100 kilograms. We got gravity down and a support force holding it up by whatever is holding it. I actually envisioned just a rope holding it. I say suspended motionless in midair. We're just going to assume that it's from a rope. So the symbol here is meant to be force up. It's supposed to be an up arrow. I apologize for my handwriting. And the first thing we're going to do is find the force of gravity on the crate. And again, to do that, Fg equals mg. You take the 10 kilogram mass, multiply it by the -10 meters per second squared acceleration of gravity, and that's going to give you a weight of -1,000 newtons down. Again, gravity always points down. So that is the weight of the crate. That is the force of gravity of the crate. It weighs about the same that I do. And given that the crate is motionless, that means it's in equilibrium. That means the net force on it is, by definition, automatically 0. Absolute guarantee. And if net force is 0, then the two forces here must add up to 0. And we can then prove that the force required to hold it up in the rope is going to be 1,000 newtons upward. So again, this is just the equilibrium state again. We're just still describing here the two forces adding up to 0. And the object isn't accelerating yet. We're now going to change that. We've got the same crate, and we are now going to increase the amount of upward force on it. If you kind of envision the crate hanging from a rope and that rope being attached to a crane, what we're doing now is we're flipping a switch to increase the amount of force that the crane pulls upward on the box. And now, as a result of increasing that force, the acceleration of the crate is going to be 0.5 meters per second squared. So we've increased the upward force, and the crate is now accelerating upwards. And with that change, now we're going to find the net force on the crate, force of gravity on the crate, and the upward force the crane is using to lift the box. Same box, very similar drawing, but now the F upwards arrow is bigger. And I've noted here, A is pointing upwards because the box is going to accelerate upwards. So, first up, let's calculate the net force on the crate. Newton's second law says net force equals mass times acceleration. We know the mass of the 100 kilogram box, and we know its acceleration of 0.5. So 100 times 0.5 gives us a net force of 50 newtons upward. So that is the net force. That is the overall total force that is causing this new acceleration. Note, the net force changed. It was previously 0, now it is 50 newtons upwards. So, if it's a non-zero net force, the box now has begun accelerating. Now, I asked what is the force of gravity on the crate, and that actually shouldn't change. The force of gravity depends on the mass of the object and the strength of gravity of the planet you're on. And lifting the box doesn't change that. I want to make that clear. An object's weight depends only on its mass and the planet it is currently on. Lifting something does not change its actual weight number. And so, nothing that has changed here has changed that weight number. The box still weighs 1,000 newtons downward, so I just copied down the same answer as before. What has changed, though, is that the net force is now 50. So the upward force will add to gravity, and they don't add up to 0 anymore. Now they add up to 50. The gravity didn't change, but the net force changed, and so if we add 1,000 to both sides to solve for the upward force, we find that the upward force is now 1,050 newtons upwards. That upward force increased by 50 newtons, and 1,050 minus 1,000 is what gives us the net force of 50. So if the net force increased by 50, then the upward pointing force had to increase by 50 to make that the case. So again, showing here that the net force is what caused the acceleration. And to find that net force, you still have to add together the unchanged weight with the now slightly increased upward force from the crane. Let's do one more example, and we'll tie friction into this one, just to kind of help demonstrate, exactly how friction works in situations involving motion. We're going to look at a horse and buggy. Buggy's being pulled down the road by a horse who is exerting a constant force forward of 65 newtons. Buggy has a mass of 150 kilograms. The buggy moves forward at constant velocity. So, first question, and this is just a concept question, why doesn't the buggy get faster? Why is it not accelerating if the horse is pulling on it? Because force causes acceleration. Why is the cart not speeding up? And it's because... hold on. It's because, yes, there is a force pointing forwards. I've got here a force body diagram, and I've labeled here force horse, 65 newtons forward. And despite that forward pointing force, the question says the buggy moves forward at constant velocity. That means that there must be some force backwards canceling out the forward-pointing horse force. And realistically, the most likely thing that would resist motion in this way is friction, because that is all friction does. Friction resists motion. Objects want to move naturally without friction's interference, but as long as this particular buggy is moving along the ground is going to exert friction on it. Friction always springs into existence whenever one thing tries to slide across another thing. Friction's a big pain like that. Objects would normally move in a straight line by themselves without any interference, but friction from the road kind of stops it. And friction is an outside force. I want to make that clear. In this case, the friction is a rightward pointing force that the ground is exerting on the buggy. It's not something the buggy's doing by itself. Friction always comes from outside of the object in question. And so in this particular case, if the buggy's not speeding up, the forward horse force must be balanced with the force of friction backwards. And similarly, since the buggy is not accelerating up or down, then the two most likely vertical forces, gravity down and normal force up, must also be canceling out. So mathematically, since we're moving at constant speed, we can again determine that net force must equal 0. And the buggy doesn't get faster and faster because net force equals 0. That means that there's a force of friction canceling out the horse force forwards. The next question is, what is the weight of the buggy? We can find that the same way we found the weight of the last couple of items. Weight equals mass times g, so 150 kilograms times negative 10 meters per second squared. This buggy would weigh negative 150 newtons downward. And now we can identify all the forces on the buggy and determine what their values are. We already found gravity, the negative 1,500 newtons downward. And we already know the amount of horse force forwards. So really we just need to figure out normal force and force of friction. And to do that, I'm going to do a net force calculation in both axes. First being the x-axis, since again, the y forces don't interfere with the x-axis. So net force x, I've just got the two x-axis forces here. That's force horse and force friction equals 0. Force horse is 65. It's adding with force friction to equal 0. Therefore, the force of friction backwards must be negative 65. Note again, it is perfectly canceling out with the horse force forwards. And this is again how cruise control works in your car. When you set the cruise control, the engine is calculating exactly how much forward force is needed to overcome friction to keep you moving at constant speed. And that's really just how you have to deal with friction in general. If you want to keep moving, you have to make sure that you are overpowering friction. Now, on the vertical axis, this one should look pretty similar. We've done ones like this before. There's two vertical forces that must, again, add up to 0. We've got normal force up and gravity down. We know gravity. We know they add up to 0, so we can, once again, solve for a normal force of 1,500 newtons. This is, again, another equilibrium state. This is net force equals 0. And now let's, kind of like how we changed the crate from being equilibrium to not, we're going to do the same thing here. We're going to end the equilibrium state on this buggy. The horse is now going to begin pulling harder and is exerting a forward force of 75 newtons. So the horse is now pulling harder forwards. And first question, we're going to answer the same basic questions, but first a different concept question. Would this directly change the value of friction from the ground on the buggy itself? Does pulling harder forwards change the amount of friction backwards? And the answer here is actually no. Pulling harder forwards on something does not actually change the amount of friction that is resisting the motion. And the reason for that kind of ties into the source, the origin of friction that I'll kind of briefly mention here. The reason that friction happens is because all surfaces are bumpy if you zoom in far enough. If you take a microscope and look at every possible surface, they are rough and bumpy when you zoom in far enough. It's just kind of unavoidable. Obviously, bumpier surfaces, this is easier to see, but even like smooth, polished metal is technically bumpy even if you have to zoom in on the atomic level. Every object just has these surface imperfections. And when one surface is, pressing into another one, when they're in contact with one another, the bumps and grooves of one kind of sink into the bumps and grooves of the other, kind of like gear teeth or saw teeth, unfortunately. And with those bumps and ridges sunk into each other, the objects don't really want to move past each other. If you've got two gears plugged into one another, they don't really want to be pushed out of each other. They're going to resist that happening. And that's what the friction is. It's just the objects resisting that attempt to shove the bumps and ridges kind of through and across one another. It's literally like trying to drag sandpaper across other sandpaper. And the things that determine friction are how rough the surface is and how firmly the objects are being pressed into each other. Pulling harder forwards doesn't change either of those things. The horse pulling harder forwards does not affect how bumpy the road is or how bumpy the wheels are. And it also doesn't affect how firmly the cart's wheels are being pressed into the dirt. Neither of those two conditions for friction change when the horse pulls harder. And so, for that reason, the horse pulling harder doesn't actually directly affect the value of friction. So that negative 65 that we found for friction before will still be the case. This would kind of be like this whole situation with the horse pulling harder is a lot like if you've got cruise control on, the car is moving at constant speed, and then you just hit the gas anyway. Like you accelerate beyond whatever the cruise control was set to. In that moment, the friction stays the same because, again, it's still the same road and you still have the same tires. The engine is just outputting more force to push you forwards. So in this particular case, the value of friction we found before does not change. And frankly, neither should the weight nor the normal force, because the horizontal horse force does not have any immediate effect on these two vertical forces. The horse pulling harder forwards does not affect Earth's gravity on the buggy, and therefore that doesn't affect how much the ground needs to support the weight of the buggy. So the horse pulling harder forwards didn't change anything else except this one variable. Now, it didn't change any of these individual forces, but it is going to have an effect on the net force. The y-axis net force is still going to be 0 because the buggy's not going to accelerate up or down in this way. Instead, what's going to happen is the x-axis net force is going to be 10 newtons forward. We've got the same 65 newton force of friction backwards, but now it's being added to 75 forwards instead of 65 forwards. And that's going to create the net force here of 10 newtons. So the horse increased its force output by 10 newtons, therefore the net force increases by 10 newtons if nothing else tries to cancel out that added force. So we've got an X net force of 10, a Y net force of 0. So overall, the net force on the buggy in this case is now 10 newtons. The net force isn't 0 anymore. And for that reason, that means the buggy is going to start accelerating. So we take that 10 newton net force, plug it into Newton's second law, plug in the mass of the buggy, and we can calculate that the new acceleration of the buggy is only 0.067 meters per second squared. So it's not a very big change. But this little change does mean that the buggy will begin speeding up for as long as the horse is outputting this increased amount of force. And again, your car works the same way. You press the gas down slightly, you break the equilibrium state, the engine's pushing harder forwards than the friction is pushing backwards, and you begin accelerating for as long as you've got the gas tapped down. And over time, that acceleration causes your speed to go up and up and up. And so all these examples are just kind of meant to demonstrate the difference between equilibrium and non-equilibrium and how the net force contributes to acceleration. And that is really all of Chapter 4. Chapter 4 is just about that one formula, net force equals mass times acceleration. And that means that when we resume meeting together in person on Friday, first I'll open the floor up to questions. I want to make sure that you guys feel comfortable about all the information we talked about today, both the falling stuff and also this Chapter 4 force equals mass times acceleration stuff. First, I'll open up the floor to questions, and then we will begin moving on to Chapter 5, which is, again, just going to be about Newton's third law. We're just kind of making our way through the laws here. So again, please let me know any questions you have. We'll resume meeting in person on Friday, so until then, send me any questions you have via email. And again, we'll have an open forum for questions in lecture as well. Be working on your homeworks for all the chapters we've covered. Be looking over these notes. Make sure that all these examples make sense. If you need help deciphering any handwriting, please let me know. And oh, I think I had another point, but I lost it. Yeah, that's pretty much it. So, again, let me know if you need anything. Thank you guys for listening and for working with me during this little weird week that I'm having. I appreciate you all, and please have a wonderful day.